we have introduced a number of proof techniques in the past videos, but there is one which is extremely useful that we haven't mentioned until now. It is mathematical induction. We consider statements Pn for each positive integer n. An example is 1 plus 2 plus 3 plus all the way to n equals n times n plus 1 over 2. We want to show that Pn is true for all positive integers n. It is clear that we can't prove them directly one by one because there are infinitely many positive integers n. However, if we can show that P1 is true, and given that Pk is true, Pk plus 1 is also true, then we have shown that Pn is true for all positive integers n. Here, P1 is known as the base case, and Pk is known as the inductive hypothesis. The idea of mathematical induction can be illustrated by the effect of falling dominoes. We can think of the statements Pn as dominoes arranged in ascending order of positive integers. Now, proving that P1 is true means that we have toppled the first domino. Also, the implication that Pk plus 1 is true whenever Pk is true means that whenever one domino falls down, it will always cause the next domino to fall down. So, since P1 is true, we know that P2 is true by applying the inductive case for k equals 1. Now, P2 is true, so again by the inductive case for k equals 2, P3 is true. This carries on for every positive integer, which means that Pn is true for all positive integers n. Let's prove the statement 1 plus 2 plus 3 plus all the way to n equals n times n plus 1 over 2 by mathematical induction. The base case is n equals 1. The left-hand side is just 1, which equals 1 times 1 plus 1 over 2, which equals the right-hand side, so P1 is true. For the inductive case, assume inductively that Pk is true for some positive integer k. That is, we assume 1 plus 2 plus 3 plus all the way to k equals k times k plus 1 over 2. Label this as star. Now, when n equals k plus 1, the left-hand side is 1 plus 2 plus 3 plus all the way to k plus 1. Applying star, the first k terms become k times k plus 1 over 2. To make it into the form on the right-hand side, we take out the common factor k plus 1 over 2. So we have k plus 1 over 2 times k plus 2, which equals k plus 1 times k plus 1 plus 1 over 2, which is the right-hand side. Hence, Pk plus 1 is true assuming that Pk is true. So we have proved that Pn is true for all positive integers n by mathematical induction. As another example, let's try to prove that for all positive integers at least 2, the complement of the union of a1 up to an is equal to the intersection of the complement of a1 up to the complement of an. This is the generalized version of the De Morgan's law for sets. The base case is n equals 2, where the left-hand side is the complement of a1 union a2, which equals a1 complement intersect a2 complement, as we know from a previous video, link in the description. So this is the right-hand side, and the base case is true. Assume inductively that for some positive integer k, the complement of the union from a1 up to ak is equal to the intersection of the complement of a1 up to the complement of ak. Let's call this star. Then, when n equals k plus 1, the left-hand side is the complement of the union from a1 up to ak plus 1, which is the complement of the union from a1 up to ak, union ak plus 1, by associativity. Now, using the base case, This is equal to the complement of the union from A1 up to AK intersect the complement of AK plus 1. Now, we can apply the inductive hypothesis star to rewrite the first set as the intersection of the complement of A1 up to the complement of AK. By associativity again, this is just the intersection of the complement of A1 up to the complement of AK plus 1, which is the right-hand side. So the inductive case is complete.